Good morning, everybody. My name is Oleg Lechak, and I will present you our article, Demodulation of the Simulated Periodical and Non-Stationary Random Signal with Hilbert Transform. I'm sorry for online presentation, but we make this presentation on June 11 because of to prevent possible power outage. The modulation procedure of the periodical and non-stationary random signals with carrier harmonics modulated by the stationary high-frequency random process were explained. One-pass filtration and Hilbert transform were used for separation of spectral components of PNRS and quadrature extraction from amplitude phase modulated signal. Its ability to extract and right estimate the quadratures of narrowband high-frequency modulation stochastic processes was demonstrated. Presented technology will be useful for vibration-based diagnosis of the mechanism. The effectiveness of investigation of the properties of physical systems and processes based on the experimental data of their behavior over time is largely determined by the ability to identify and evaluate their main characteristic features. These features are obviously the repeatability and stochasticity of their behavior, and these features appear in the properties of the processes, not independently but in interaction. Many processes in geophysics, meteorology, radiophysics, signal, and technical mechanics are characterized by its behavior. Periodical non-stationary random processes are mathematical models describing the complex interaction and repeatability and stochasticity. The methods of analysis of such signals processes should obviously include in their structure both periodic functions and purely stationary random processes, both extreme cases and various models of the interaction of periodicity and stochasticity. Vibration signals acquired in machines and mechanisms during diagnostics are one example of such processes. Vibration signal can be modeled as the superposition of harmonics with multiply frequency, which are stochastically amplitude and phase modulated. Simultaneous simulation of PNRP signal as well as its demodulation procedure involving Hilbert transform are presented in this article. For simulation, we select the following known model, where omega 0 is the base cyclic frequency, lambda 0 is a central frequency of high-frequency modulation stochastic process. The quadratures of modulating processes have a following form, equation number 2 and 3. Assume that quadratures in 2 and 3 have different autocovariance function and are non-correlated. The covariance function of signal in 1 is equal to the following. Let us assume parameters for simulation of PNRP signal. For a simulation of PNRP series, the following parameters were used. AP equal 10, AQ equal 4, alpha P equal alpha Q equal to 0.01, omega 0 equal to 100 multiplied by P, lambda 0 equal to 2000 multiplied by P. And the series length was 50,000 points. A fragment of the simulated series is shown in figure 1. The estimators of the covariance components were calculated using the following equation and are presented on figure 2. As we can see, the forms of estimators' behavior and their values have insignificant differences from their theoretical values. Substituted in equation number 4, 5, and 6. Now let us obtain the Hilbert transform for simulated PNRP series. Calculations of estimators of covariance components based on the Hilbert transform for series confirm that the differences between the values of the covariance components for the signal and its Hilbert transform are negligible, and we can see it on the figure number 3. The zero spectral components for series was estimated using the following equation. Here K is a Hamming window. L L and UM is the cutoff point of parallelogram. The graph of F0 shown in figure to explain two clear peaks. To separate two spectral components of PNRP signal visible on figure 4, we use bandpass filtering with rectangular transfer function. The obtained filtered signal can be represented in the form equation 7 and 8, where zeta plus and zeta minus are upper and low frequency bands respectively. The estimators of the covariance function for the signal in series in equations 7 and 8 are slowly decaying harmonic oscillation as it is presented on figure 5, the frequencies of 850 Hz and 1040 Hz. Tiny estimator values will coincide with theoretical ones calculated by the following equations. The values of the second component estimators for the time series in equation number 7 and 8 for the arbitrary leg are smaller than 0.01. Thus, the separated spectral components of signal in 7 and 8 can be considered as a realization of stationary random process. Note that the sum of their autocovariance function is equal to the zero covariance components in equation 4. The cross-covariance functions signal in equation 7 and 8 are calculated as following. It is clear that it is symmetrical. Using the following statistics, we can estimate the second cosine and sine harmonics for a cross-covariance function of signals in 7 and 8. Adding these quantities, we obtain the estimators of the covariance components, signals in 5 and 6, respectively, as it is shown in figure number 2. A Hilbert transform of the processes in 7 and 8 gives following, and then we can extract of their quadratures using following equations. The segments of quadrature time series are shown in figure 6. The estimators of covariance function of the quadratures for zeta minus spectral band are presented on figure 7. These are slowly decaying functions. Small differences between their values and the theoretical ones, which were determined by the following relations, can be explained by the statistical errors of calculations. The modulation of the simulated periodical non-stationary random process with Hilbert transform-based procedures proved that it is possible to extract quadratures of the modulation processes and estimate their covariance properties with statistically satisfied accuracy. Such processing technology can be useful for the modulation of the complex vibration signals for diagnostics of the mechanisms. Thank you very much for your attention. Zlatan.